time to wake up. It's 2:50. It's like 3 o'clock.
So we're trying to collide, for instance, a 2,1 hydrogen with a 3,2 helium and get them to turn into a 4,2 helium and a 1,1 hydrogen. So we're effectively taking these two small nuclei to make this bigger one, and this a leftover proton that kind of pops out the side. What are the difficulties we've got to overcome in making these two things collide?
Hot.
It's got to be. Why is it got to be hot? Because what is heat? What sort of energy?
Kinetic energy.
When we say hot, we mean high temperature, right? What does that mean? High what sort of energy?
Big fast.
High kinetic energy, fast particles. Why? Why do they go fast? Why can't they go slowly?
Because I am speed.
Why do we need them to be going fast for them to collide?
Overcome binding energy.
Oh, because they repel each other.
Because they're both positively charged, they're both going to repel each other, and so for them to overcome that Coulomb repulsion and get so that they're effectively touching, so that the reaction can take place, they have to be going really fast, which means we need a really high temperature. How high? Kind of like the sun. Like this is the nuclear reaction that happens on the sun.
5 million degrees.
5 million degrees?
Yeah.
Okay, because I don't have a number in here.
Or something like that.
The other problem with things that are going really fast is that generally the density goes really low, and so to have a high enough concentration of these particles for the reaction to continue, it needs to be high pressure as well. So on the sun, we really easily tick these boxes by the gravity of the sun providing the pressure to keep these particles close enough together that they can react, and then the temperature of the sun, which comes from the fact that it's got a nuclear reaction going on already, is what gets these particles moving at a high enough speed. And so the difficulty that we've got to overcome to make fusion happen like on Earth and to harness this as an energy source is finding a bottle that will hold it, finding something that will withstand the high temperature and provide the pressure that we need in order to keep these particles together for long enough and moving fast enough for the reaction to happen. And we're up to a few seconds at the moment, like people are using magnetic fields and lasers to confine the particles using not physical boundaries but using like pressure waves or using a donut-shaped magnetic field to contain these particles in a region so that we don't have to build a material that can withstand like conditions on the sun. So fusion is really appealing because it doesn't produce any radioactive byproducts, and we only need a tiny little bit of very common material to burn, but it's really, really technologically difficult to overcome. Fission is much easier. Fission, we can just use stuff that we've got on Earth and put it kind of close together and it reacts, but we get all these radioactive byproducts. We've got to bury it or shoot into space or something. So we want to be able to do fusion, but we haven't got it working